computer, I've kind of changed a few of the slides around a little bit. But I want to kind of go back to where we were near the end yesterday and just quickly run through that with you. So, so we were talking about the biostratigraphy, and said that during periods of slow sedimentation, like you might find during deposition of a condensed section, a big shale, that you're going to get a relatively high concentration of these dead microfossils as they fall through the water column. And much more so, the organisms in the water column, they don't care what's going on on the seafloor. So the accumulation rate is the same in both cases. So if you have a high sedimentation rate, you're going to have fewer relatively fewer of those fossils than you are during periods of a low sedimentation rate. And periods of low sediment input or sedimentation rate are when you have your condensed sections forming. So if we look at a well, for example, and here we have a vertical well here, and we do our sampling for our microfossils like I talked about yesterday, and the paleontologist starts looking and identifying the different fossils at different depths, going from the bottom to the top, and counts the number of each particular fossil at each horizon. And like in this case, what was found was these intervals here. This is a planktonic planktonic organisms, and you find various intervals where you had a high abundance. We call that an abundance peak. High abundance at certain depth intervals in a well. And the same thing as other type of fossil called a nanofossil, same thing. You found various intervals that had high abundances or abundance peaks. And in fact, there were 6 of them found in this particular well. And the names of the particular organisms are here: Annula, Garocapsa, Celii, so on. So some of those we know when they became extinct from past studies. Paleontologists have determined when some of these microorganisms started to evolve and when they became extinct. So we usually, some of these then we can actually put an age date on. We usually, by convention, we use the extinction age, the age at which the organism became extinct, and we use that as our absolute age. So now we can assign some absolute ages to these different horizons. And again, we call those abundance peaks. And some of them are sometimes age datable. And what I said then is what you'd really like to do if you're going to do some mapping to try to correlate some of these intervals, you really want to, or you should, if you have seismic available, you should transfer these depths at these abundance peaks to seismic time, two-way travel time, which is the vertical axis in seismic. And I said there's ways to, there's equations by which you can convert depth in a well to two-way seismic travel time on a seismic section, and vice versa. You can take two-way seismic time and convert that to depth. So here's an example where we had some abundance peaks. Go to my highlighter here. We had an abundance peak here on our log, and another one here, another one there. Big abundance right down at the bottom of the well. And so we can, this now is the in depth, but now we can translate that into two-way seismic travel time, and we see that certain abundance peaks have high amplitude seismic reflections associated with them. Not all of them, like this one here, doesn't, but this one's a very nice sharp amplitude for this particular abundance peak. Yeah.
On what does it depend if it gives you good amplitude or not?
Well, it basically it's where you have a change in rock type so that your petrophysical properties are different. So you might have a sandstone and a shale, okay, and because the properties of the sandstone, let's say the acoustic velocity is different between the sandstone and the shale. So at that interface, you'll get a reflection. And the greater the difference in the petrophysical properties, the higher will be the reflection amplitude. Okay?
Okay, so we can say that in that specific place where there is a big amplitude and also there is a lot of fossil.
Right. Well, what you do is, well, that's basically correct, but see now this is in depth. This is one of these, this column right here is kind of like that column there, where you've got depth, and these are planktonic organisms here, so we get our abundance peaks. And you see there's several of them in this particular well. Those abundance peaks are because the abundance peaks occur in intervals with slow sedimentation rates, like condensed sections. Usually what these high abundances indicate are condensed sections. And the condensed sections are shaly with organic, so their velocity is slow, their density is low compared to, say, a sandstone. So where you might have a high velocity, acoustic velocity, and a high density. So when you get that contrast, if it's sufficiently different between one rock and the other, that surface, you'll get your seismic reflection. Okay, and if we assume now that wherever you have these abundance peaks, they represent condensed sections, we're actually, when we make this conversion, we're actually identifying from the amplitudes here, we're identifying abundance peaks, which are condensed sections. And that's what you want to put on the seismic, those condensed sections. That's what you want to go in the seismic, so that you can map away from the wellbore. You basically calibrate your well and find all of these reflections, and then you overlay this onto your seismic section, and you'll end up, you can end up something like this, for example, where here's your seismic section, here's a well, and we knew that one fossil called Lacanosa occurred at this depth in the well. And we know that Lacanosa is found in a condensed section. So what I've done here, I've taken this green line, I've been able to tie that green line or that seismic reflection right here. So So I can now map it away from the well bore, and there it is right there. So, especially if I've got a 3D seismic survey, like we do in this case, we've now been able to map away from the well bore the condensed section. Remember, your condensed section is your seal rock and it's your source rock. Okay, so now we've got some valuable information on our seismic that we've taken from one well and expanded that in 3 dimensions from our 3D seismic survey. Okay, so Lacanosa, we found another fossil called Gyrocapsa at this depth in the well. So I can put this green line here represents another condensed section. That's showing up. So that's another condensed section. We also found another one that we had no fossils, but we felt it was a condensed section by looking at the well logs, and that one occurred right through here. And then we had, let's see, so this one was Gyrocapsa, and we had this other one, an organism called Celii, and that corresponded to this reflection right there. So now we have found 4 condensed sections, and I put them in here, these green lines that refer to the seismic reflections that correspond to the condensed sections. So now we've been able to identify 4 source rocks, hydrocarbon source rocks, and 4 potential seals. Now, if you think back to the sequence stratigraphy, what occurs below a condensed section, stratigraphically below a condensed section? Well, if you're in deep water, you're going to get a submarine fan deposit during that falling stage of sea level. And let me do it this way here. So if we have our sea level curve here, during the falling stage of sea level, in deep water we have deposition of submarine fans, and in shallow water where you guys do all your work, we've got an erosion surface, one of those transgressive surfaces of erosion that I talked about. And when does the condensed section form? It forms right in here on our sea level curve. So that being the case, if we've been able to map our condensed sections on the seismic, we can predict what's going to be below. If you're looking in an area, a geographic or geologic area, that you know there's deep water deposits, well, where are you going to look in your seismic line for those deep water deposits? You're going to look below the condensed section. You're going to look below the condensed section, okay, because this is the horizontal axis on our curve is time. So this is older time and younger time. And then overlying that will be your condensed section. In shallow, that's in deep water, you'll get the submarine fan overlain by the condensed section. In shallow to non-marine waters, say in fluvial systems, if you get deposition right about in here, say backfilling of your incised valleys occurs on this part of the curve. So once again, your reservoir potential is going to be in the rocks just beneath the condensed section, slightly younger. So what that means then is that I can look just below the green lines here that I've drawn in, the condensed section, and that's where my potential reservoirs are going to be. Now, quite often these potential reservoirs give you high seismic amplitudes, very large amplitudes, and they show up as very distinct seismic reflections. So, for example, let's take Lacanosa here, and on the seismic we see some high amplitude reflectors just beneath the condensed section. Well, we can also go and look at our well log, and what do we see in our well log? Here's the Lacanosa horizon where we found Lacanosa, and what have we got? We've got a nice sand just below. So this way, it's like I said yesterday, if the boss comes in and says you've got till tomorrow morning to pick out 3 drillable sites, and you say, I've got this 3D seismic survey, how am I going to do that? Well, you want to kind of high grade or eliminate areas that probably are not potential for reservoir rocks. And so you can do this procedure where you define the condensed sections, and then below the condensed sections, you're going to have potential reservoir, either like in sites valley fills or in shallow water or in deep water submarine fans. And stratigraphically above, you're going to have your big progradational deltas. So you take that model and you predict that by defining one horizon here, you can predict what's going to be above and what's going to be below. So you cut down your time enormously, the time it takes to do your interpretation. Okay, so let's leave it at that for now. So I went through then how do you read these biostratigraphy charts. I went through the triangle yesterday, where the triangle signifies the point on the left, the sequence boundary, on the right, the sequence boundary, and here would be your maximum flooding surface, would be the tip of the triangle. So we went through this, I'm not going to go through this again. So we get to our chart here now, and you say, Slatt showed us how to build a sequence stratigraphic framework from the seismic, but I don't have the time to do it, or I've forgotten how to do it, or whatever. So you can go to one of these charts that have been made for your area, specifically for your area. And like I said, most places you'll find these charts in company files, or you can, like in the U.S. Gulf of Mexico, you can go out and buy one of these for $200. And you can read you can develop your sequence stratigraphy just by knowing the fossil. So here's Lacanosa again. This chart is geological time on the vertical axis. So here's 1 million years, 2 million years, 2.5 million years, and so on. 1.5 million years, and so on. Well, we know from past studies that Lacanosa was deposited 800,000 years ago, 0.8 million years ago, according to what you see in the parentheses here. So we go to our chart, and we go to 0.8 100,000 years, and that corresponds to this arrow, and it where it crosses the triangle, it crosses right at the peak. So we know that Lacanosa then represents a condensed section. So we can go back Say, okay, Lacanosa, a condensed section. And now, not only do we know the type of deposit, in this case a condensed section, and that can be, for example, an unconventional resource shale or whatever, or other types of mud. But now we also have been able to put an age to that horizon, 800,000 years. So that green line represents deposition 800,000 years ago. Same thing here with, let's look at cellei. We find cellei at a depth in our well. There it is there. Its extinction age was 1.35 million years ago. So there's cellei here, 1.35 million years ago. And when you follow the line at 1.35 million years, that also is at the peak of the triangle. So it too represents a condensed section and maximum flooding surface. We look at, let's say we found the Gyrocapsa at some depth. And we know that Gyrocapsa became extinct 1.15 million years ago. We go here, and it's a little bit off here now. Not quite on the peak, and it's not quite on the trough here. So we have to make a geological guesstimate as to what it might represent. And in this case, I would pretty much say it represents a condensed section as well. So we now have a seismic line that we've been able to put age dates at different horizons. And also we know we've identified those horizons as condensed sections. Not only that, but we can look below the condensed section, and where you're apt to find sand is going to be below the condensed section. Either if you're up on the shelf or non-marine, it'll be a non-marine sand body. If you're in deep water, it's going to be a deep marine, submarine fan sand body. And we can verify that by looking at the log, where Gyrocapsa, for example, corresponds to a big thick shale, right there. That's our condensed section. And what do you find below it? A nice big sand body. So it's all predictable. So when the boss says, you know, you got to be ready by tomorrow morning with 2 drillable prospects or something, you've been able to cut down considerably where you look on the seismic, where you look for reservoir, source rock, and seal rock. Remember, I defined sequence stratigraphy the other day as identifying reservoir, source, and seal, and that's what I've just explained, how you do that. So, I've got an example here. So let's go to a well, and here's a well. We'll call this well number 1, where we have identified Lacanosa at this, up to this depth, Gyrocapsa, and cellei. Okay, so that's what we have on the log, and we know the age from our chart here. We know the ages of those 3. the last age of deposition before they became extinct. 800,000 years ago for Lacanosa, 1.15 million years ago for Gyrocapsa, and 1.35 million years ago for Celii. Well, now we can do a couple of things. If we've got seismic, we can go through this process that I've been going through, and we can go to other wells, and where we have a seismic reflector, say that represents Lacanosa, we can find that on, with the seismic, we can map that horizon around, maybe to where well number 2 is, and we find Lacanosa there. And so now we've been able to correlate from one well to the next. And so if you've got another well number 3 here, you can do the same thing. Now this one, Lacanosa was not found in this well, so you have to kind of use your log response, and that would be something like this. So let's go to the seismic line then. So here's that well number 1. Okay, and here is the well tied to the seismic. So Lacanosa is right here in the well. Gyrocapsa is right here in the well right there. And Celii is right down there. Okay, so now we've got our 3 horizons again, and we can map away from the well that particular reflection that represents the Celii interval. We can do that for Gyrocapsa. We can do that for Lacanosa. Okay, and even if you cross faults, I think there's a fault right here, you can usually still pick up those reflectors. So now we've been able to really make progress because we've been able to use our seismic to map away from the well bore. So I'm going to make a little chart here, and for well number 1, here's Lacanosa. It occurs to a depth of 3,980 feet. We know the age. Gyrocapsa, the depth is 9,680 feet, and Celii is 10,850 feet in the well. And I could do the same thing for these other wells. Other wells here, using the same procedure. So I make a chart for well number 2, well number 3, well number 4, well number 5. So now I see if I want to map Lacanosa around, we use the seismic to map that Lacanosa horizon around, and we find that in well number 2, Lacanosa is at a depth of 3,820. Well number 2 didn't have any biostratigraphy analysis done on it. So well number 3, well number 4, Lacanosa is at 3,730 feet. And well number 5, Lacanosa is at 3,756 feet. So we now know, we've now been able to go to 4 wells and find that relative horizon that correlates with each other. So we have Lacanosa And we go to our chart and find out on well number 3 what depth is Lacanosa, well number 4 what depth is Lacanosa, and well number 5 what depth is Lacanosa. And so we put those depths on, and it turns out like that. So we've now been able to make a correlation. We do the same for Gyrocapsa. To make a correlation. We do the same thing for Ciliae. And we can make our correlation that way too. Now, this is the, oh, okay. Well, what I want to do is, give you a chance to try your luck at biostratigraphy analysis at the reservoir scale. What I have is an example here. This is a real example from the North Sea, and where you had 4 wells. Well number 4, well number 3, well number 2, and well number 1. Well, these wells, there's a stratigraphic datum that I hung those 4 wells on. So what I ask you to do is spend a few minutes correlating the sand bodies. This is in an actual reservoir, and they wanted to do a water injection, a water flood. And so they tried so what they did is they brought their geologist out to do some correlations. And the geologist picked this stratigraphic datum and then correlated the sand bodies. So why don't you take a few minutes and see if you can correlate those sand bodies? Okay? Looks easy enough, at least for well number 4, 3, and 2, looks pretty easy. We've got a big shale here at well number 1, which caused a problem, but go ahead and try to do a correlation.
Este más grande parece este mismo. Estos así, que aquí no se vería, y este más grande.
Entonces aquí tenemos acá. Y este es este. Y este es este. Y este no se ve. ¿Esto es de la empresa o de uno? ¿De la empresa es este?
¿Cuál?
¿Tu máquina?
No, mía. Esto ya no se ve. Aunque hay este cuerpito de araña aquí, pareciera este y este. Y ahí comienza otro más grande, que debe ser más arriba. Creo que no se ve esto. ¿Es este?
Pero aquí, ¿no? Este es bien brusco, aquí es. Tiene una pendiente.
Sin estos son más marcados. Aquí, aquí y aquí. Este no tanto.
¿Qué le pasa?
¿O será este? No, no.
Ya se lo preparó doña Neta.
We got them all
El 4 este es
correlated.
de agua.
Esto no va a ser.
Hagamos.
Esto es un. Estás reduciendo tu grado. ¿Cuándo es de golpe?
¿Cómo estás?
¿Cuándo cae de golpe?
Tiene que ser un cambio de ambiente.
En todos cambian, ¿no? Te
Parece que
cambia
los
todo
dos
el radar, chapo.
parece que van de 3 a turnos.
De loco.
Sí. Para empezar, ni siquiera están a la misma profundidad. Ah, por el dato.
No salta.
Así está por el dato.
Los datos de ahí no están. No coordinación. La ubicación necesitaríamos también.
Debe estar tal vez de sur a norte, aunque no está 4 3 2 1, está claro que no
Puede
ya.
estar como si.
Puede ser.
Pero también podría ser.
El well en el ruso, luego torrente de arena grande.
Y aquí igual viene, sube pero vuelve, que tiene una variación. Que no se ve en esta bolsa.
But you got it figured out? Correlations? Yeah, possibility, yeah.
Aquí podría ser con esta.
Sí.
¿Verdad? Así podría ser incluso. No, ahora sí, pero esta no.
Tal que son más profundos, ¿no?
Could be a fault, yeah, could be a fault. Okay.
O estos planos, o son bloques. Aquí es el canal. Con esta sección.
Sometime I'll sign up before the end of the day. Okay, so after lunch, sign
Son
on, take
envidiosos.
5 minutes.
Eso me gusta, ¿eh?
All right, well, I think most of you did a pretty good job of correlating the sand bodies, but when they started the water flood, what they did was the idea was to inject water into well number 4 here, into the sand body, and then drive more oil to these wells, at least well 3 and 2. Well 1 seems to be something missing here. Maybe there's a fault or something, possibly. And but the water flood was a failure. They injected into well number 4 and waited for some breakthrough, and there wasn't any. And they waited and waited and waited forever, and nothing happened. So it was a failed water flood. Well, so they had a meeting and said, the meeting mainly petroleum engineers, and so my gig here now. And there was one geologist in the room, in the back, way in the back of the room, you know, the geologist there, and said, well, I don't see any, in your correlations, you didn't do any paleontology. Yeah, right, ooh. And so, the geologist said, can I take a look at this? It's kind of a junior geologist, you know, with the company. I said, can I take a look at the paleontology report? And everybody looked around and nobody knew where it was. But somebody, so the geologist went and looked around and finally found the paleontology report, all dust covered, you know, and everything else. No one's ever used it. So he did that, and what I've done here now is, and you don't have this one on your computer, I don't think, and the paleontologist, what I've done here is I've kind of condensed the report. The report was several pages long, but what I've done is condensed it down, and what was found in the paleontology report is that there were 4 groups of fossils. This group had 3 different fossils, again those Latin names. There was another, we'll call those Group A. There was another with 1 fossil that was a diagnostic fossil, we'll call that B. This one had Margaritae and Rhombolodiscus, call that C, and then E. There's no D in this for some reason. So, and there were some fossils there that were diagnostic. And the paleontologist noticed that the last appearance, from the bottom to the top, the last appearance of these fossils were at different depths in the well. And so made a chart, and in well number 1, we had Group A at this depth, Group B at this depth, Group C at this depth, and Group E at that depth. Then in well number 2, at that group, that depth, and so on. Well, because these groups represent specific intervals of geological time in which these particular organisms evolved and then became extinct. And so they're time correlative. You can correlate them. Remember what I said when I first defined sequence stratigraphy? It's a correlation based on time, geological time. So here's an example of that. So why don't you go back now to your cross section and put in for well number 1, put in A, B, C, and D at those different depths. Do the same for well number 2, well number 3, and well number 4, and see how they correlate now on the basis of time intervals at which these organisms live. And see how that compares now to your previous interpretation.
1741 en el vuelo 1.
Okay, so I think hopefully you can all see that there.
En 1894. Abajo.
No, pero del mismo color le pondremos aquí.
Por eso. En el 2, abajo. 1894. No hay.
No, no, eso es zona.
1894. Luego ¿de dónde sacaste ese 1800?
En el 2, fue el 2, tipo 1A. Todas las artes
ya.
tú pones junto a los dos.
1830.
So you've got, it's kind of hard to see the depth, but you can see the depths here if you've got your computer. So the question is, why was the water flood a failure? You can answer that with this paleontology data.
Pinch out it, ya sabes. La comedia.
Professor, but sometimes when we have the palynology data, when we use the palynology data, sometimes we have the markers so big.
Oh, good. Okay.
Sometimes we cannot make this type of exercise because, for example, I don't know, one sport that's
and if you're working in fluvial, you don't have the fossils. Yeah. But if you don't have the fossils, you don't have the fossils. You can't do anything. But if you do have the fossils or a paleontology report, you ought to use it. Yeah. Glad that you do. Well, that's right. The scale of the fossils too. The age scale, the age range. Yeah. So, and that's why you try to find fossils that you know that the age range is limited. Yeah. But see, this is a reservoir scale now here. Now, we're not using absolute ages here, but what we're doing is we're defining periods of time in which different fossils lived. So we're not using absolute ages here, we're using this strictly for correlation and at the reservoir scale. Okay. This is only, each one of these wells is about a mile apart. So it's a reservoir. We don't know in this case the absolute age. This is an old Pennsylvania age reservoir. And when you go back that far in geologic time, you often don't have much in the way of fossils. But, so we don't know the ages. But in this case, what we want to do is correlate the rocks that have those particular fossils. And then there's four groups, A, B, C, and E. So You know why the water flood failed?
Okay, so if we look at the
Okay. You know why the water flood was a failure? It's all right in front of you. Why was the water flood a failure? Remember, you were injecting water into well number 4.
yeah,
Where did that water go?
down.
Yeah, it's not going to go across. Why? Because the sand in well number 3 isn't the same sand. Where you correlated before, you correlated because the logs look the same. You correlated the sand at well 4 and at well 3, but they look the same, but they aren't. Time-wise.
Yeah, I mean they. So I mean, that's it looks so alike. Like we really see
Yeah.
them.
But it's not. This is a real example of the North Sea.
So if we don't have access to paleontology, we don't.
No. But if you do have access to paleontology, you should use it. No, you're not doomed to failure without paleontology. One thing you can do, I just mentioned the first day, I think, a little bit, palynology is useful, where you look at these pollens and spores that are derived from plants and terrestrial vegetation, and you can use those the same way. You get different types of spores and pollen from different trees and grasses, and so you can correlate them.
We do have
Me parece medio
paleontology.
extraño, ¿eh?
Somewhat.
We have
Así,
paleontology.
con los
Palynology? Yeah, well, that's
Este igual hay
why.
They
uno.
only give us the age of the
Well, yeah, but it gives you the age, but it also allows you to correlate just like this. We're not, there's no absolute age here that I've given you. What I've given you is groups of organisms that lived at different times. And it doesn't matter the age. I didn't give you any absolute age. You didn't need it. So you can you follow the force the same way.
We just have to see if the lab has the capability to even those.
Well, yeah, you have to have, just to, again, you don't need the absolute ages, as long as you can find out what groups of pollen. If you got one group here and another group there, just like this, it's the same principle. And it's pretty successful for non-marine reservoirs, fluvial reservoirs. So it's not deposited at the same time, it's not the same, so it's not correlative. Why is the water flood a failure? Why didn't the water get to that?
Bueno, estaba la parte. Ida y vuelta como el mar.
Well, what is that really showing you there? You've got a shale here,
En vivo.
shale there. That's a shale.
No se
So
puede
you've got a
tener.
shale barrier. That's why the water flood was a failure. Could be, yeah.
Son dos astronautas, no sé de dónde son, pero son de la ISS, entonces tal vez uno es canadiense.
Venían.
Venían en el espacio.
Okay, well, let me give you the answers here. your first correlation might have been something like this. This is what there's variations, but really the important thing is that most all of you, I'll bet you, correlated this sand, one sand. And then here you can do over here you can do any couple of different ways. This is the way I correlated it. And so the idea would be that you inject water here in 4, and the water goes into 3, the sand there, and you can put a fault here maybe, or maybe it's just a stratigraphic pinch out. The fact that you can correlate up here, these beds suggests maybe there's no fault there, that it's more of like a stratigraphic pinch out, something like that. And, but whatever, the key here is these 2 wells here. And so when the water never got to well number 3, something happened to the water. It just didn't evaporate or anything. And this is the second correlation you did with the biostratigraphy, and that would be the correct one. You had the group A fossils deposited in the sediment at a particular time. Now, I haven't told you in absolute ages what the time is. It doesn't matter in this case. What's important is knowing that you had a group of fossils that were deposited during a period of time, and then those fossils became extinct and another group came in. So you got another group, group B, and then the fossils became extinct, and you got another group, group C, which is the green one there, and then they became extinct and you had group E. So where did the water go? Well, the water, what this is really telling you is that see this shale right there? Shale right there? Well, you have a correlation there from the paleontology, so you had a shale break there. And the shale was thick enough and had the proper properties that it wouldn't allow the water to go through. So rather than the water going this way, it got to that barrier and it stayed in this zone here. Never got across. And that's why it was a failed water flood. Now in this case, I didn't have to give you absolute ages. All you needed to know was that there was a period of geological time in which this specific group of organisms lived. These right there. And then another time interval where that organism lived, and these had become extinct by then. And the same thing, another interval there, and another interval there, and I called them A, B, C, and E. So this was an incorrect correlation with the paleo. That was the correct correlation. Now somebody said, you know, we usually don't have paleo because of paleontology because we're working in non-marine sediments. And that's true. These are marine fossils, and in non-marine sediments you don't get many fossils preserved, like in fluvial systems. But there's a field called palynology that I just kind of mentioned briefly the other day. And in fact, I'm going to go back to that. Let me give me a minute here to go back to that. remember I talked the other day about this reservoir here, and I was talking mainly talking about the seismic, where you could see these nice point bars. Whoop. Where you can see these nice point bars that were mud plugs, and what I just mentioned in passing was you could use these were fluvial, but they had in them the palynology, which is pollen and spores. Now, pollen and spores come from plant material, terrestrial plant material, trees and grasses and weeds and things like that. And they often form in distinct groups that become, when they say the trees become extinct and another group of trees, a more advanced group of trees starts to evolve, you get a different set of pollen and spores. And so it's the same principle as this exercise just did, but it's making use of the palynology in this case. So what you do, it's pretty simple, the procedure. You just take your cuttings or your core or whatever, and you dissolve out the matrix, and you concentrate all these little things that are different types. And a specialist called a palynologist that can identify these. Maybe some of them are age datable, and maybe they're not. But if you can identify them, then you can do the same sort of thing as you did with the example you just had. Same principle. As that. Okay? And here we use marine fossils, but in a non-marine setting, you look for the pollen and the spores. And then in that case, you look for a palynology report, not a paleontology report, but a palynology report. And do the same sort of thing, use it for correlations. So there are organisms or organic material that can be used for correlations. Another example of that is that sometimes you'll drill a well, sometimes you'll drill a well, and sometimes you'll drill a well and you do the geochemistry of the well, you do Rocky valve or TOC or whatever, and you find that you've got oils that aren't the same, or gases with different compositions from one well to the next. So you drill a well here, you drill this well, and you sample it for the geochemistry and the chemical composition of the oil. And so you determine the chemical composition, and then you go to the next well over here, and you determine the chemical composition, and you're expecting it to be the same, but it's not. Different oils. And this is one of the reasons why you often get that. different oils because of this compartmentalization. So what that means often is that one oil migrated into the sand, and then at a later date, another oil migrated into the other sand. So when you see a case like that, where you've got two wells with the composition of the oils or the gas is different, then you've got a good chance that you've got that compartmentalization. And then you look for why you have the compartmentalization. In this case, it's because you have a shale break. Now, one other thing to point out, just get rid of this. One other thing to point out is that the unit, the A group is older than the E group, and so does this tend to be a high stand, a transgressive, or a low stand reservoir? Anybody? What's it doing? You're getting younger in that direction. Well, land is over here, sea is over there. So is that a high stand, a transgressive, or a low stand? The high stand is prograding. Okay? So you've got prograding sediment, and it could be deltas. These could be fluvial sands associated with delta and with a marine influence, and that's why we have the marine fossils. So, see how valuable that paleontology is, or the palynology in your case, where you can do the same things with the pollen and spores. Okay, we did this exercise earlier this week, where the two choices were one that you had a single sand body, and that was incorrect. And what was correct is that you had a series of sand bodies, transgressive sand bodies that were migrating from landward. So we won't go do that again, but here's a problem for you. Here you've got a well log, and see if you can interpret the sequence stratigraphy from that well log. Things you want to look for are, well, it says here flooding surfaces, okay? But one of these flooding surfaces is going to be stronger than the others, and it's going to be what we would call the maximum flooding surface. It's the most intense one, the most landward extent of the shoreline. And when you find that one, what would you expect to find? When you find the maximum flooding surface, what would you expect to find above it and below it? And you can make those predictions. So spend a few minutes interpreting, doing the sequence stratigraphy of this well log. First thing you want to do is find the maximum flooding surface. That's going to be your marker horizon. And then what do you see above it and what do you see below it? Interpret the whether you've got low stand, transgressive, or high stand deposits.
No.
No.
¿Tienen ese slide?
41.
41. Cuestiones muy diferentes.
No tenemos. Otra cosa tenemos. Ese es.
Maybe I didn't give you that one.
Number 41.
43. No. Este, ¿no?
I'll give you a hint that you're in a shallow environment, up on the shelf, and even possibly fluvial. You're not out in deep water. So interpret the sequence stratigraphy.
Aquí tienes canal. Aquí tienes.
No sería por acá.
TCT.
TCT. Y este el